Hello, everyone. Hey, let's talk about some transition metals and some pretty cool transition metal chemistry. So let's go over to the PowerPoint slides. Start the slideshow. Maybe. There we go. Cool. And coordination chemistry. We'll explain coordination chemistry in just a second. First, do the transition metals. You guys know they're the middle block here. Where's my pen? Well, I don't need the pen. Scandium here, element 21, the zinc, element 30, those 10 elements across, and then everything down count as transition metals. Ooh, let's go back one slide. Do you remember how to set up the electron configuration? That's where you, I do need the pen. That's where we say, hey, the periodic table is the guide to helping us position all the electrons within an atom into their orbitals. We said that the first two columns count as the S block. The last 6 columns count as the P block. And the D block constitutes the transition metals here. And then down here is the F block. You can't remember that? We'll just do one real quick. Here's scandium, element 21. So what we think, in order to do the electron configuration where you assign every electron to an orbital, is we say that, hey, scandium comes in as an element with equal number of protons and electrons. So yes, it's element 21 with 21 protons. That's what makes it scandium. But in the neutral atom, it also has 21 electrons. So where are those 21 electrons? Well, the first electron is in the same place where the first element's electron is. Hydrogen has simply a 1s electron. And the way you can get that from the periodic table is that you're in the first row, so the 1 of 1s, and you're in the s block, right? And then every orbital, an s orbital, a p orbital, a d orbital, they can hold 2 electrons. So when we're playing the electron configuration game, we kind of have to put helium here. Element 2 should be right over here because the second electron of scandium goes in the same orbital that the second electron of helium, where it goes, is in the 1s orbital, right? So there's electron configuration for helium. And then if you want to do the electron configuration for lithium, the third electron has to go into the second row, a 2, and it's still in the s block, a 2s. This look familiar? Yeah. And then the fourth electron finish filling this 2s orbital. The fifth electron through the 10th is in the second row, so it's a 2. That's the principal quantum number. And you're in the p block. And we need, well, it's electron number 5, then 6, 7, 8, 9, 10. Let's count how many electrons are in the p block. This is 1 electron, 2 electron, 3, 4, 5, and 6. So we need to get 6 electrons to be 2p electrons, and then we pair them up. Well, it turns out there's 3 orbitals. Each orbital holds 2 electrons. Yeah. Okay. And then we go down to sodium, and we're still heading for 21 electrons of scandium, and we found the first 10 electrons. So let's do electron number 11 and 12. Well, we're back in the s block on the third row. And then we go over here, electron 13 through 18 are the 6 electrons of the, well, third row, 3 p block. And we got 6 electrons because there's 3 orbitals that each can hold 2. And I'm not filling it correctly, right? The proper way is to put 1 electron into each orbital and then pair up. The reason for that is that electrons repel electrons, right? So it takes some energy to force them to pair up into the same orbital. It kind of crowds them out. Okay, then after that, we finally get to potassium. And that's element 19 and 20. We're back in the fourth row, S block. And then we're going to scandium. Hey, There's a 21st electron. It's in the 4th row, but here's the exception. The D block doesn't start with 4D, it starts with 3D. So you go back one level, one row number, I guess you'd say. So it's really the 3D orbital that actually gets one electron, the 21st electron of scandium. So here's the full electron configuration for scandium. And then there's a shortcut, right? If you put a noble gas in brackets, argon in this case, what we're saying is, hey, think about all the electrons that make up argon, all of these. Well, next time we draw this out, we won't draw every single electron. We'll just say, hey, go get the electron configuration of argon, and then just start from there. So after you take care of the 18 electrons of argon, just put in brackets, then go to electron number. Why is that a 1? Oh, that's right, because they switched these. Sorry. So let me finish the thought first. If you wanted to do scandium the shortcut way, which I advocate, it's a good idea. Find scandium here, then go back to the nearest noble gas. And instead of writing all of this out from 1s to 3p, just write AR in brackets. And then know argon took care of 18 of those 21 electrons. So now you only have 3 left. Electrons 19, 20, which I would put in the 4s, and then I would skip over to the 3d. Now on the slide, they switched them. And the reason for that is the 4s orbital is a higher principal quantum number. That's the 4th shell. It's higher in energy in the sense that it's farther away from the nucleus. So that's why they put it last. Now on the test, if you drew it 4s, 2, and then 3d, 1, or you switch the order, I would give you full credit. Okay. The next slide is going to ask us to do electron configuration for chromium and copper. So let's clean this up. Go to the next slide, please. There we go. Okay, the expected configuration, right. I should have grabbed the periodic table. Let's go back one slide. So how many d electrons do we predict for chromium here, right? Well, let's just do it. Where's my pen again? So if we're going to do the electron configuration of chromium, let's take the shortcut. There are 24 electrons, but let's take care of the first 18 by just saying, hey, someone else can go work that out. What's the electron configuration for argon? We're just going to say someone else already figured that out. We're just going to carry on with with electron number 19 and 20, which is the 4s. And then we're in the D block now, electron number 21, 22, 23, and 24. There's 4 electrons that are 3d electrons. That's what we expect. Nature, she makes all the rules. Let's do copper. Copper is going to be a similar scenario. We're going to say, hey, electron configuration of argon. So will take us all the way to electron number 19. Electron 1920 are 4s electrons. And then to get to copper, there's 9, right? 21, 22, 23, 24, 25, 26, 27, 28, 29. That's 9 electrons. Start on scandium, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So our prediction should be this. It turns out we're wrong. These are the 2 you need to memorize. That we're actually, when we do this little counting rule with the periodic table, we come up with the wrong answer. So what we expected is here, and we just did that, right? 4s2, 3d4, and copper, we said 4s2, 3d9. Well, what nature says is, hey, this higher shell, why don't you slide 1 electron over, and then we can half fill the d orbitals. And there's something stabilizing about that. What's more stabilizing if you can fill the entire 4D shell by doing the same idea. Start with what we predicted, 2 electrons in the 4s. Let's just have 1 electron slide over. And now the entire D block, sorry, the 3D set of orbitals are all filled, and that's really stabilizing. Remember that the noble gases have full shells. Yeah, all of their orbitals are filled. And so right now, copper is feeling a lot of extra stability because the 3D orbitals are all full. And in terms of quantum numbers, this is higher in energy. The 4s, there's only 1 electron where that's just more stable, having the electrons in the lower orbitals. Okay, so memorize chromium, copper. We'll be using those from time to time. Right, we had the elements here. Let's go into ions. So if you need to figure out what the electron configuration of an ion is, get the neutral atom first, then take away electrons if you're making cations. And that's what we're doing here. So we got iron, there's electron configuration. We could have used the periodic table to get this. And then if we want the 2+ ion, take away 2 electrons. Well, remember, nature's kind of lazy. She wants to make the most stable atom. And if you imagine an atom with, the 1s shell, and a little bit bigger is a 2s, and a little bit bigger is 3s, a little bit bigger is a 4s, the 4s is on the surface. And so if you have to reach down and grab the electron and pull it away, it's easier to grab the electrons on the surface, which are the 4s electrons. Even though when we did a little periodic table, little game there, we put the 4s electrons in first, and then we did the 3D next. Doesn't matter. Doesn't matter how we filled the orbitals. What matters is that you start with the complete iron atom, and now we want to take away electrons, and it's easier to take away the electrons on the surface before we take away electrons farther in and closer to the nucleus. Closer to the nucleus, the more tightly held or attracted those electrons are. Just because protons are in the middle, positive charge, electrons are negative, right? So on the surface, they're easier to peel off. So to make iron 2+, lose both of the 4s electrons. And if you want iron 3+, we'll now go after the 3D. And among all these electrons, these 2 electrons are paired up, are repelling each other. So it's almost like they're trying to kick each other out. So if you want to remove 1 electron, remove 1 of these. And then that leaves the D block, the set of D orbitals, half filled, and that's stabilizing. So Fe3+ is actually a quite stable ion because it has these half filled D orbitals. But the takeaway message is, when making cations, set up the element in its natural state, remove the 4s electrons first, and then unpair electrons, and then just keep taking away electrons till you get to the charge that you need. Iron 3+ in this example. Okay, let's give it a go. Let's go to another application so I can draw a little more easily. Hopefully make it a little more clear. There it is. Okay, so I just copy and paste it over here. The question, I got a periodic table. That'll make it helpful, make it easier. Okay, so we need to write electron configurations of each of the atoms or ions. And let's get a little more space here. Let's take away this block. Right, so nickel is here, element 28. Chromium is element 24. Copper is element 29. Good. I didn't erase too much of the periodic table. Get my pen back. Good. All right. Hey, nickel. Start with the shortcut. Nickel is element 28. Going back to the nearest noble gas, that's argon. And then electrons 19 and 20 are in the 4s. And then to get the nickel from the D block, I got 1 electron, 2, 3, 4, 5, 6, 7, 8. 3D8. Done. Let's do chromium. Okay, so the question asks for chromium 3+. It's a good idea to just do neutral chromium first. Again, we're going to start with argon. because there's supposed to be a column here saying, hey, chromium, what's your electron configuration? Start with argon, put in the 4s. That took care of electrons 19 and 20. And then to get the chromium, it's 1, 2, 3, 4. So that's what it's supposed to be. But chromium and copper are the exceptions. So cross that out, and it's actually slide one of the s electrons over. If you want to put a 1 here, you can. Emphasize there's only 1 electron in the 4s. But more importantly, there's 5 electrons in the d. And the d orbitals are half filled. This is the 4s. This is the 3d. There's 5 3d orbitals, and each one has an electron now. And whether you draw the electron configuration this way or this way is your choice. Cool. Wait, we're not done with the question. That's the neutral atom. So now to go to the chromium +3, take away electrons from this one. So remove the outermost electron in the 4th shell. So the 4th shell is empty, so I'm not going to draw it. It's going to leave me with the 3Ds. I already removed 1 electron. To get the +3, I need to remove a total of 3 electrons. So take away this one, and then I'm just going to start at this end. There's nothing paired up, so I'm just going to take with this one and that one. The ones I've circled have been removed, leaving behind these 3 electrons, and we're done. That's electron configuration. Or argon 3d3. Your choice, however you want to draw it. Let's do C with copper. First do the neutral atom before we go to the cation. It's argon. And then the way I would figure it out, I know it's an exception, but my brain is just like, okay, what's the normal way of doing it? 4s squared. And then the 3d, well, how far do you get to copper? It's 1 electron, 2, 3, 4, 5, 6, 7, 8, 9. It should be 4s squared d9. Wait, there's only 1 more electron necessary to fill the d block, and that's what nature says. Yeah, let's go ahead and do that. Leaves 1 electron in the 4s, and the d block gets filled up, at least on the 3rd row. Cool. That's a neutral atom of copper. And then you want to go to copper plus, so remove 1 electron. Well, it has to come out of the s block first, the 4s, the higher shell. So there we go, argon 3d10. Nice. Back to that learning check. Cool. What we got here, oxidation potential. So it's a tie-in, just tying in to, transition metals are found on that standard reduction potentials chart when we were talking about electrochemistry. You know how to read that. I don't think there's anything new here. They're pointing out in this slide that, hey, transition metals can have various oxidation states. Scandium and zinc are pretty standard. They just have one charge. Like the rest of the elements, the main group elements, like magnesium is a +2, sodium is a +1. They don't have other oxidation states. Transition metals, however, can vary, especially like manganese, chromium, and iron. They have lots of and vanadium. Yikes. You can't predict it. You need to have more information in order to know what its oxidation state is. Here's manganese again. Look at this. We got +2, +3, +4, +6, and a +7. There's permanganate. It's got the characteristic purple color. And depending on its oxidation state and what else it's attached to, we'll discover, can change its color. That's kind of cool. Anyways, that's an interesting fact. We'll dive into color later in these PowerPoint slides. Okay, so here's the main objective, coordination chemistry. So the transition metals can actually form covalent bonds to what we otherwise would think of as anions, like magnesium. Sorry, yeah, let's go back one. So we got magnesium as a +2, +3, +4, all the way to +7. And we have some covalent bonds to oxygen here and the hydroxide ion. Although the hydroxide ion, no, maybe not. That's just a regular counterion. Turns out that the oxygens in MnO2 and especially permanganate, it's one of the polyatomic ions we have to memorize. Even though we have a metal with a nonmetal, and normally that should be ionic bonding, it's not. For the polyatomic ions, those are covalent bonds. And specifically, when you start attaching the transition metals, which have a positive charge, and covalently attaching other things, that's called a coordination complex or coordination compound. So the proper definition is a compound which is a central metal atom or ion is attached to a group of surrounding molecules or ions by coordinate covalent bonds. So there's that coordinate word again. So just think of coordinated, like joined together, but mainly it's a covalent bond. And every time you have a new idea, here comes some new words. So a ligand or a ligand, however you want to pronounce it, those are the molecules or ions that are covalently attached. A ligand donor atom, those are the atom that specifically found the ligand that's making that covalent bond. So as a good example, gosh, what is it? We'll see that in the next slide. Maybe I'll point that out, what a ligand atom donor atom is. Coordination number. This definition says the number of ligand donor atoms that surround a central metal atom in the complex. It's easier to think a coordination number as the number of covalent bonds to the metal ion. Here's some good examples. So where's my pen? Okay, so let's talk about, let's do the coordination number first. So let's draw this. So what's going on here with Ag, it's a cation, and then there's two ammonia molecules that are stuck to it, covalently bound to it, 3. Okay, so the number of covalent bonds is 2, or there's 2 ligands, 2 ammonia molecules attached. Okay, so the coordination number is simply how many covalent bonds does a central transition metal make? Although it's not always transition metal. Aluminum can work too, and so can lead. Technically, they're not transition metals. But anyways, the number of covalent bonds, that's one way to get the coordination number. You also count the number of molecules, but we'll see that's a problem in a minute. So it's better to count the covalent bonds. There's 2 covalent bonds here, 2 attached groups. The ligand donor atom, for ammonia, it's nitrogen. Nitrogen's the atom that's bonding to the transition metal, not hydrogen. So for ammonia, you'd say, what's the ligand donor atom? It's nitrogen. Nitrogen's making the bond to silver. Let's go over here to, how about chromium with 6 water molecules? So we got chromium, and then there's a water molecule up here. Maybe I won't draw it like that. Let's draw it like this. There's one down here, and it turns out the ligand donor atom is oxygen. Oxygen is making the covalent bond. There's another one away from us. Remember, the dashed line means it's fading into the distance, so it's going back and behind us. And then there's a water molecule coming out. That's supposed to be a wedge bond, sort of like a 3D-ish bond that's coming out of the screen towards us, where the water molecule is attached. And you can see I've attached 4, that's 6. I've attached 6 water molecules to chromium. That's what it tells me to do. So the ligand number, or the coordination number, is 6. There's 6 covalent bonds, or 6 ligands, however you want to say it. Cool. All righty. What's the next slide say? Stop that and go on the next one. There we go. Oh, they drew them for me here. Oh, okay. So you can count. So when we're looking at coordination number, it's better to count the covalent bonds, but You can also count the number of attached molecules if there's something called monodentate. Dentures, dental cream, sounds like a tooth. And that's the idea, that these molecules bite with one tooth, what? They attach with one bond. That's what it's saying. So ammonia is a monodentate. It attaches one time, one covalent bond. So is the chloride ion, it's monodentate, biting once. Water, biting once. It attaches to one covalent bond. Another idea about the donor ligand atom. Let me say that right. Ligand donor atom. The atom that's making the covalent bond. So in the thiocyanate, you can see sulfur has a negative charge, 3 lone pairs. It's going to donate one of those lone pairs and attach through sulfur most of the time. So the sulfur atom will be the ligand donor atom that attaches to the metal ion. But nitrogen also has a lone pair. So there are times when nitrogen becomes the donor atom. It's the bond, sorry, it's the atom that makes the bond to the transition metal. Okay, you don't have to memorize these. I'm just pointing them out as examples. All of these can attach to a transition metal. And it's a covalent bond, right? So that's kind of weird when you look at copper with 4 chloride ions. What's going on here? Well, that's a covalent bond, even though each chloride started out with a negative charge. See, that's what you can kind of think of. This chlorine is -1. There's 4 of them. So the chlorines contribute a -4 to the whole molecule, the whole complex. And yet there's a bracket here saying, hey, this one molecule has a net -2 charge. Wait, how can that happen? I thought the the chlorides, there's 4 of them. So doesn't that give you a -4 charge? Yeah, but copper has some charge too. And together, x -4 has to equal the net charge of -2. X -4 equals a -2 charge. So add 4 to both sides, and you get that x equals a +2. This is a copper +2 cation with 4 attached covalently bound chloride ions. And together that makes one molecule called a coordination complex or coordination compound. And together it has a net negative charge of 2. So if you put this in water and you evaporate the water and make a salt out of it, this will pick up 2 counterions that have positive charge. So maybe there's some sodium around. You'll pick up 2 sodiums that will balance the -2. The sodiums don't get covalently attached. They're ionically bound, just like in table salt. Let's see, what's a -2? How about oxygen? Right? So in the compound sodium oxide, Na2O, ionic bonds hold the sodiums next to the oxygen. In this compound Na2, let's see, how's this go? Yep, goes copper ion first and then the chlorides next. This compound says, well, no, inside the brackets is one molecule that has a net -2 charge. That's what's attaching ionically to sodium. But inside that molecule, there's 4 chlorines that are bound covalently to that central metal atom, the copper. Okay, monodentate, all these ligands, they attach to the transition metal through one covalent bond, and that's it. There are other molecules, however, go ahead, that attach more than once. So poly means many. So we had mono meaning 1. You could have a didentate, or is it bidentate? Meaning 2. Polydentate's a general term with more than 1. So we have this very common molecule. I don't know if you can read it on the screen. It's ethylene diamine, abbreviated EN, ene. And there's 2 nitrogens. Each nitrogen can attach to the metal atom. Glycinate, that's actually amino acid. Nitrogen and oxygen can both attach. It's bidentate. There you go. There's a term. It can bite twice. It has 2 teeth. Bidentate. It can attach twice. The oxalate ion, 2 oxygens. This one's really cool down here. This is ethylene diamine, tetramine. Wait a minute. Ethylene diamine tetraacetic acid. Sorry, I got this silly bar on the screen. There we go. Okay. If you look on some cereal boxes and on other packaged goods, you might see this as an ingredient, EDTA. And what's happening is this is a hexadentate, 6 teeth. There's 2 nitrogens and 4 oxygens. And all 4, this whole molecule will roll around a central atom. That's not really showing it here. Maybe there's some other pictures later. This one molecule can bite down 6 times. It can make a total of 6 covalent bonds to the central atom and essentially just cage it up. So why is it a preservative? Well, a lot of bacteria and mold and fungus, they need some metal ions. So like minerals, vitamins and minerals to do their chemistry, to replicate, to grow. And so if you add a little EDTA, if there's any metal ions in solution or in the food, this will bind them up and make it difficult for the bacteria or the mold to actually get that metal ion that needs as a nutrient and slows down their growth. Thus, it's a preservative. Cool. Oh, here we go. We got ene, ethylene diamine, bidentate, has 2, they call it chelating agents. Another word for the polydentate ligands. They can bite twice. Now we're not talking about teeth. We're thinking of a crab with pinchers. The pincher has 2 points of contact. And you can see that this ethylene diamine, 2 carbons, 2 nitrogens, it can bind twice and make this one molecule can attach through 2 covalent bonds to the central atom. And you can see that there's 3 of these molecules. Whoops, let's go back. 3 molecules. Wow, too far. 3 molecules in total attaching to a cobalt central atom. Now we can go over here. Here is one of the molecules that makes life possible, right? So this is hemoglobin, found in red blood cells. If you take out the iron, the molecule is called heme. That's what's at the bottom of the slide. With the iron, it's hemoglobin. No, I'm not so sure. Here we go, EDTA, ethylene diamine tetraacetic acid, all bound up, wrapped around a single metal ion, binding 6 times. Cool. Okay, and then this stuff you've seen before in Chem 25 when you talked about molecular geometry, electronic geometry, shapes of molecules. Yep, so we got linear, tetrahedral, square planar, octahedral. So we'll be using those terms again. This time, however, talking about ligands being attached to a transition metal. Oh, other coordination geometries, that's not on the test, but hey, it's kind of interesting shapes. Naming coordination compounds. Okay, so there's some rules here, a lot of procedure. If you're a chemistry major, I really encourage you to get these rules down. But to get through this class, we're just doing an introduction, right? So I just want you to get the main idea. So why don't I read through these rules, if you will. We'll do some sample problems. Where I will give you those rules in a little more clear form. Yeah, and just the nuts and bolts of what we really need. Okay, so here are the rules. We'll just kind of go through them, and then we'll practice using a condensed set of rules so you can see exactly what you need to know for the exam. Okay, here are the rules. If the compound's a salt, name the cation first and the anion second. Sodium chloride, we've been doing that before, so it doesn't matter. Once you get to the more complicated transition metals, if it's a salt, it has to have a cation and an anion. The cation goes first. Okay, when you're naming one of these transition metal complexes, maybe a complex ion, or it could be neutral, whatever. It's got all these ligands attached. When you're naming it, put the ligands first, then the metal. So we're naming it with letters and words. ligands go first, and it turns out it's in alphabetical order. The names of anionic ligands end in O. I will give you names of ligands on the test. That's a nice pattern. They all end in O. Neutral ligands, well, they have their, they say the usual names. So I'll give you the list. I will give you the unusual names for water. It's aqua. So if you know some Spanish, agua. Change the G to a U and you got aqua. You already know this is ammonia, but we're going to call it amine. We'll see that in a minute. And this is carbon monoxide, the molecule, but when it's a ligand, it's called carbonyl. Again, I'll give that to you. Yeah, and here's the list, but it won't be in this form, but that's the information, right? Mention the carbonyl group, CO, water is aqua, agua, aqua. Here's ammonia, it's amine. Ammonia, AMM, amine. Again, I'll give that to you. You don't have to memorize it, but it makes sense. We'll see oxalate ion. So it'll be oxalato, hydroxide definitely, and all the halides will be common ligands. Cyanide's a common ligand. I don't see thiocyanate too often, but there it is. Okay, rule 3, if the complex contains more than one ligand of a particular type, indicate the number with the appropriate Greek prefix. So if there's 2 amines, you say it's diamine. If there's 3 amines, it's triamine, right? So mono, you don't say the mono. You say diamine, triamine, tetraamine, and then it's pentaamine, hexamine, right? You had to learn those prefixes when we named salts last semester or whenever you took the first semester of general chemistry. So the same Greek prefixes. Maybe I'll give that list to you in a second. The ligands are listed in alphabetical order. Prefixes are ignored. Right. So if you have diamine and aqua, where's my pen? I'm not so good at listening. I see better. So if you have a compound, transition metal complex, that has 2 of the ammonia molecules, you're going to say, well, the ammonia molecule has the name of the ligand is amine. 2 of them is diamine. And if it has 1 attached water molecule, then it's agua, aqua. I'll give that to you. You can just look on the sample test and get the name. And then it says put it in alphabetical order, but don't do it in terms of the prefix. You're going to alphabetize it by the A, break the type of the next letter, M before Q. So this is going to go first in front of the aqua in the name. So don't use the ditritetra when alphabetizing. And remember, the ligands go in alphabetical order, but not with the ditritetra prefixes. And then this little thing, you won't have to worry about this one, but this is interesting just in case you run into it. Let's see, we had the ene has the name ethylene diamine. Again, you don't have to memorize it. I'm going to give it to you, but it already has a di prefix in it. So if the name of the ligand itself contains a Greek prefix, that means you can't use it again. So what happens if your molecule has 2 of these? You would have said, well, if it has 2, you're supposed to use di, but I already have di in the name. So in that case, you have to use these special prefixes, bis, if you have 2, and tris, and tetrakis. Sounds kind of romantic. Anyways, that's where those names will come up, and you'll see them from time to time, but you don't have to memorize them. Just out there. Next slide. There we go. Ooh, remember when we were naming ionic compounds before and you dealt with transition metal? In the name of the transition metal complex, you have to report the charge of the transition metal as a Roman numeral. So that is still true here. So use a Roman numeral in parentheses immediately following the name of the metal so you can capture the oxidation state or its charge. And then it turns out that, transition metals are typically cations. Well, they have a positive charge or a positive oxidation state. But if they attach a whole bunch of negative ligands, the whole net charge might be negative. And if that's the case, then we use the ending 8 at the end of the whole name to represent, hey, the whole thing has a net negative charge. You remember the 8 ending, like in sulfate and nitrate, oxalate, permanganate. Those are a whole bunch of anions. So we're just following the same pattern. Cool. And then down here, again, I'll give these to you if you need them, or just make your best educated guess. The weirdest ones are the silly little banner here. Can I move this? No. There, good. Yeah, zinc is zincate. Yeah, the C. Manganese is manganate. That's pretty straightforward. Nickel, nickelate. That makes a lot of sense. But iron, it's not ironate. You have to go back and use the Latin word ferrate. And gold would be aurate. Aurate? Aurate. Anywho, that shows you how often I use that word. Not often at all. Okay, but again, you don't have to memorize these. If you need them, I'll give them to you, or we'll take off any points for spelling. But if you see ferrate, that's pretty common. Just know that that's iron. And right, the atomic symbol for iron is Fe, so that'll be helpful. Okay, I think we have some sample problems. Yes, let's go look at those. Over here, so I can mark up the screen. Okay, let's see, a cobalt ion, cobalt 3 plus 3, oxidation state ion, forms a complex with 4 ammonia molecules. Okay, so let's jot some of this down. We got the cobalt plus 3, and it's going to attach 4 ammonias. So you should know the structure of ammonia, and if you don't, there we go. This is the top of your sample test. This will also be the data you'll get on your next exam. So right in here, the spectrochemical series, we'll explain that in a minute, well, a few minutes. You scan it right here. Here is ammonia, NH3. And here are the names. You don't have to memorize them. I'm going to give you this just in this form. So CN is cyano, NO2 minus is nitro, ene is ethylene diamine, and then NH3 has the name amine. That's the ammonia molecule. We got water next is aqua. Okay, so what have we got? We got 4 ammonia molecules. So you're looking at the top of the sample test. If this was an exam question, look at the top of the exam. You find NH3. And 2 chlorides, well, you should use the periodic table, which you'll get. And you'll be able to predict that some -1 charge, the halides are all -1 in their normal ionic state. Okay, what's the formula complex, including its charge? Okay, so when you're writing the formula, you list the metal first. And then I'm not going to take points off, but traditionally, you list the neutral ligands next, then the negative ligands. And you're not going to see any, but there are some positive ligands. They would go last. But you're not going to see any in this class, I don't think. I don't intend to. So that's the plan when you're drawing the complex. Also, you put things in brackets to indicate, hey, this is the part of the molecule that's covalently attached together. That is my coordination complex. And so this whole cobalt ion with 4 ammonias and 2 chlorides is the complex, covalently attached molecule. So let's list the metal first. Just like down here is an example of a formula. We don't list any charges unless there's a net charge at the end. So I know the cobalt's +3, but don't put it here in the formula, right? When you write table salt, that's formula table salt. This is not, right? You don't list the charges in the chemical formula. You don't. Okay, it's got 4 ammonias, so put ammonia in parentheses and put a little 4 down there. Say, yep, got 4 ammonias. In chloride, leave off the minus sign. And you don't have to put parentheses around this single atom, this single formula, right? Just put a 2 there and then grab it, put it all in brackets. And then it says include its charge. It really means the overall charge. So what's the total charge on this thing? Well, The cobalt's a +3. Each chlorine is a -1. So we got a +3 and we got a -2 here. That gives you a net +1 charge. So the whole thing is covalently bound together, but some of these groups come in with charge, and the net charge, just add up your charges. Put it outside the bracket, and you're done. If you put this in the water, you would need to have a counter ion. So maybe another chloride ion, it's possible, that's not covalently bound. So the plus with the minus will neutralize it. Okay. What's the oxidation state of platinum in this coordination compound? Okay, so we got our brackets. What's this K out in front then? Well, it's not covalently bound. If it was, it'd be inside the brackets. Nope, that K, well, you get a periodic table. So if you don't have potassium memorized, it's right here, element 19. It's an alkali metal. Alkali metals, one valence electron, like to lose that electron and become a +1 cation. And that's what it is. This potassium is +1. So that tells you the whole other complex, the whole other thing, must be a -1. Cool. What's the charge on ammonia? Well, it's up here. It has 0 charge. It's neutral. What's its charge on the chlorines? They're all -1. So there's 5 chlorides here. And there's a net charge of -1. And then platinum has some charge of X. We have 5 negatives, so -5 equals a net -1 charge. Add 5 to both sides, and X is a +4. That platinum is a +4 cation inside this complex. With 5 attached chlorides, the net charge then is a -1. There you go. That's the oxidation state. It's a +4. Ooh, I don't think that's next, is it? I forget. Let's go back and see. Go. There we go. It is. Should have went back. Darn it. What's next? There's 4. Okay, good. All right. Back to the other screen. Let's see. So just to reiterate, I think we're good about listing formulas. This is the most important part here. Put the metal first, inside brackets, list it with the ligands, neutrals first. Ammonia didn't have any charges, neutral. Chloride had negative charge, listed next. Oxidation state, just work backwards, figure out what the counter ions charge are, whatever, how many there are, and then they'll tell you the charge of the whole complex. Then look within the complex to find those charges. Working backwards, you can figure out the charge of the metal, the oxidation state. Ooh, let's name them. Okay, so let's name this thing. Okay, so when you name it, it's reversed now. You want to put the ligands in alphabetical order. Alphabetical order. Then the metal. Then charge as a Roman numeral. And then if overall is negative, you add 8. Okay, so we got this molecule, it's cobalt, we got ammonia, we got chloride. Let's get the ligands in alphabetical order first. Inside the brackets are the ligands, and there's 6 of these. So what is NH3? It's right here, NH3. It's the 4th one in the series, so the 4th name is amine. How many are there? There are 6. So how many sides in a hexagon? 6 sides. This is hexaamine. And yep, just cram hexa right next to amine. So the coordination complex inside brackets, that's it. I've named all the ligands. The ligands go first, alphabetical order. Yeah, there's only the amine. Then the metal, so it's cobalt. And if you don't know how to spell cobalt, go to the periodic table. You'll get that on the exam. CO is right here. It's C-O-B-A-L-T, cobalt. Read it off the periodic table. And then I need the Roman numeral for its charge. Okay, so now we have to work backwards. What are these chlorides doing outside the bracket? They're all just counterions. They're all just negative charged chlorides. Why are there 3 of them? Because the whole complex must have a +3 net charge. What's the charge on ammonia? Nothing, 0. So inside here, the only thing with charge is cobalt. That must be +3. It is. Roman numeral 3. Cool. Is this whole thing a net negative charge? Nope, it's a +3 complex. So don't add 8. And this whole thing is a cation. So we're naming salts, and that's what we have. We have this cation here, a +3 cation, and then here are the anions. And what's the name of that anion? Chloride. Do you remember when we had to name this molecule? Way back when life was simpler? This ionic compound was magnesium chloride. Did not say di. Why did we get away with leaving off the di-tri-tetra? Because you could use the periodic table to discover that magnesium is always +2 when it's ionic. Chloride is always -1 when it's ionic. And the only way to make a neutral compound is to have 2 of these here, right? So in the name, you didn't need it. Still true here. Breaking down this name, you can figure out this whole thing has a +3 charge, so it requires 3 chlorides. So that's a little tricky when you're naming these coordination complexes. For the ligands, you do need the di-tri-tetra. If it's inside the brackets, you need it, hexa, because it means inside the brackets, but outside you don't. Okay, what else we got? Another compound. We got RH. Go to the periodic table. That's rhodium. Ooh, I deleted it. No worries. I got a backup periodic table over here. Rhodium is element 45. RHODIUM. Okay. Down here. Okay, but we're going to name this. We're going to name this compound. So ligands first. This one is ammonia, but it's been called amine. The I, well, it's the last one in the series. It's iodo. Oh yeah, it ends with O. These I2s are outside the complex. Let's save those for later. So iodo, there's only 1. There's 5 of these. The Pentagon's a 5-sided building in Washington, D.C. So this is pentaamine. And then alphabetical order. But again, don't use the penta when alphabetizing. It's A before I. So the name is going to be pentaamine iodo. RH is rhodium. And then Roman numeral. Oh, wait. This is the time I need to put in the 8 before the Roman numeral. But what's the charge on iodide when it's outside the bracket? Straight off the periodic table, it's a -1. Okay, so this complex is positive. Doesn't have an 8 ending. Rhodium 8, nope, just rhodium. The charge though, let's figure that out. There's 2 extra iodines outside, right? So there's an I- and I-, and then the complex. So the complex must be a +2. Inside here, there's an I- covalently attached, and the ammonias, which have no charge. So the rhodium and the iodine together, so rhodium, I don't know its charge, iodine I do, it's a -1, together they add up to +2. If you like algebra, it would be x minus 1 equals 2. Add 1 to both sides, x is 3. Rhodium is a +3 again. 3 minus the iodine's charge gives you a net +2, and that balances out the iodide's outside. Ooh, iodide's outside. That's called iodine. Nope, it's iodide. Sodium chloride, sodium bromide, sodium iodide. Yeah, there you go. That's the name of this compound. Got another one here. Pause the video and give it a try. See if you can name it. Inside the bracket, you got water and ammonia. Water is aqua with a aqua with a G with a Q, A-Q-U-A. And amine in alphabetical order comes first. So I got 5 of those again. So it's pentamine, 2 M's. Whoops, I misspelled it over here too. Should have 2 M's in there, sorry. Pentamine, and then aqua. And it's rhodium again. Iodide is negative, but now it's a -3. Water doesn't have charge, ammonia doesn't have charge. The whole complex has a net +3 to balance the 3 negative iodides outside. So rhodium must be +3. Yep. And then outside, got the iodide, no di, tri, or tetra. Doesn't matter, it's outside the complex. Nice. And scroll this up a little bit without losing my chart up here. So, ooh, okay. So this hasn't been updated. I forgot to cut and paste it. I am working on your sample test. So here's a copy of sample test. And here I did include CO carbonyl. So I'll make sure you get this version, not the one I cut and pasted onto a little worksheet over here. Because we need that. So CO is carbonyl, and there's 5 of them. So pentacarbonyl. And then this is Fe. Where's the charge? There's no charge. Where's the counterion? There's no counterion. This is a neutral complex. What is that? Carbon monoxide, the carbonyl ligand, has no charge. So neither does iron. The Roman numeral, I guess, is a 0. But that's, you're supposed to report the charge, your transition metal. And that's it. That's the whole name. Weird. Any more? Yep. Okay, C2O4. Go back to the top of the period of the sample test that you'll get. And it's not here. Darn it, I didn't update it. It's on the other one. Go back over here. There it is, C2O4 right there, 2-. It's actually one of the polyatomic ions. You know it better as oxalate. But the ligands usually end with an O, so it's not oxalate, it's oxalato. Sounds like gelato. Now I want some ice cream. Okay, how many oxalatos are there? There's 3 of them. So that's like a tricycle has 3. Tri-oxalato, and sorry, the spelling was on that other handout, which you'll get. Just have to find C2O4 on that chart. There's oxalato, 3 of them. And then iron, ooh. But what's the overall charge of this complex? It's negative. So we're supposed to do iron 8, but that was the exception. This is the ferrate. So make your best guess. Just remember iron is an exception. So not iron, use the, is that the Latin, ferrate? Then do the charge. What's the charge? Well, the oxalate ions each have a -2 charge. There's 3 of them, so together they all add up to -6. The net charge is -3 though. So x minus 6 equals -3. X minus 6 equals -3. Add 6 to both sides. X equals a +3. X, iron, is a +3. So isn't that weird? So the iron has a positive charge, a positive oxidation number, but because the whole complex ended up negative, that required us to add the 8 ending. Cool. All right, learning check number 4. Let's go the other way. We got the name. Let's crank out the formula. Now in the formula, the metal goes first. Well, maybe not. We got potassium. What's the charge on potassium? It's a +1. Use the periodic table. Tetracyano. Okay, so the cyano group is right at the start. Well, not on yours. You'll have the carbonyl group first and then cyano, but CN minus. And how many of them? Tetra. Like Tetris, the game, has 4 blocks. Yeah, there's 4 cyanos, and there's a gap here. So my complex doesn't have potassium attached. It's tetracyano. Nickelate, well, the whole thing has a net charge of, well, a net negative charge. But nickel's the actual metal ion. What's the charge on the nickel? It's a +2. Okay, so now let's write this in the proper form. Inside the brackets, you're supposed to list the metal first, and then the ligand. There's only one type. There's 4 of them, and the brackets. And then this is going to have a net charge of what? Well, there's 4 minuses here, and that's a +2 equals the overall charge. Well, that's a -2. I'm not going to put it over there. I'll just put it out here. If the whole thing has a net -2 charge, then how many potassiums do you need? To balance that, you need 2 of them. And there's the formula. Remember, no plus charge, minus charges in your chemical formula. If you need to put them in there, like you're saying, oh, wait, but this is a -2, minus, and then I'll need 2 of these. Okay, but then over here, make it nice and neat so I understand that. You understand that in the formula, there are no charges listed. And you put a box. There's the proper answer. And if you show your work over here, I'll be like, okay, good job. But you only get full credit if you draw it that way, leaving out those charges. Okay, next one. Aqua, that's water. Chloro, that's Cl minus. Bis, I know that's weird, but that means 2. A bicycle has 2 wheels. Bi, 2 ethylene diamines. That's just the ene group, and you have 2 of them. Bis, ethylene diamine, and then cobalt with the charge of +3, and then there's a space with a bunch of chlorides. So this makes up my complex, and then there's extra chlorides to balance the charge. Don't know how many. We'll figure it out. Maybe we'll figure it out now. Water doesn't have charge. Chlorine does, and there's only 1. If there were more than 1, it would have said dichloro, trichloro, hexachloro, whatever. There's only 1. Ene is neutral. If you go up to this chart, Cn minus, NO2 minus, ene, no charge. NH3, no charge. H2O, no charge. Okay, so you don't even have to memorize it, just look. So OH minus, F minus, excellent. That's cool. So just go to the top of your exam, you'll see that, and just use it. All right, so no charge here, no charge in water. So we got a -1 and a +3 equals the net charge or the overall charge. Well, then that adds up to +2. So we're going to need 2 of these. in our formula. Just like we needed 2 potassiums. Okay. All right. So let's put this in the proper form. It goes brackets and then the metal first. And then the ligands, it's supposed to be the neutral ones first. So water and the ene. And then if you just put them in this order, I would give you full credit. But the proper way of doing it is the neutral ones first. And there's two of them. So I think you're supposed to go alphabetical order, aqua before ethylene. So there's the water. Here's the ene group. You can put in parentheses 2. And then there's a chloro. Oh, sorry, there's 2 enes. Almost forgot that. It's a bis, ethylene diamine. And then the chlorine, it's the anion after the neutrals. Finish my bracket. That's what the complex is made up of. And then there's 2 chlorines on the outside. Done. Sodium, Na+, hexa, fluoro. Means we have 6 fluorines. And we have aluminum, 8. Okay, so the whole thing has a net negative charge, but more importantly, it's aluminum. Hey, where's the Roman numeral? You don't need one because aluminum's not a transition metal. So go use the periodic table and predict its charge. Aluminum, where are you? Column 3. 3 valence electrons. So lose those 3 and become a +3 cation. There's aluminum. So aluminum's a +3. +3, and that's it. This is my bracket. That's my complex, 6 fluorides, 1 aluminum. How many sodiums do I need? Well, there's 6 minuses, and there's a +3, and that equals the total, or the net charge. -6 + 3 is a -3 charge. That's why the 8 is here, and we're going to need 3 of those sodiums. So Na3, then the bracket, the metal first, then the ligands, and we're done. Diamine, 2 amines, 2 ammonias. The silver, where you can go up to the periodic table and look up the name silver, and you'll discover Ag is the chemical formula. It's got a net the silver ion has a +1 charge, but ammonia doesn't have a charge, so that's also the charge on the whole complex. And that's it. We got silver listed first. There's 2 ammonias, and there's a net +1 charge on the whole ion. Nice. Okay, hope that makes sense. We spent some time on naming, so definitely that'll be a portion of the next test, naming, either going from the name to the formula or taking the formula back to the name. Cool. We're in isomers now. Isomers, those are compounds with different molecules with the same chemical formula. That's how I name it, or I remember it. Compounds with the same formula, but different arrangement of atoms. More importantly, they're different molecules. That's crazy. They're made up the same atoms, but if you attach them a different way, they're new molecules. They're different from each other, but they have the same chemical formula. There are different ways to make these molecules different from each other. There's constitutional isomers, where you're actually just physically attaching molecules in different ways. Stereoisomers, the connection you make are 3-dimensional. That was a little more subtle. When you're connecting them by different ways, there's linkage isomers, ionization isomers, and those diastereomers and enantiomers. We're not going to go into too deep with the stereoisomers, but here, let's just introduce these different isomers. Okay, look at the bottom of the cobalt complex. The donor atom is nitrogen, right? This is a nitro group, a nitrogen with 2 oxygens. It's on our list. It has a net -1 charge. But here the nitrogen is attaching the cobalt. But you can also have the oxygen attached, and the color is different. So that alone tells you these are different molecules. It's got the same atoms, same chemical formula, but it's a constitutional isomer because one way you connect through the nitrogen, Another way you connect through oxygen. Different, and it's also linked differently. So these are linkage isomers too. Okay, so linkage isomers, that's a term I want you to know, and that's where you link the atoms differently, either through nitrogen or oxygen in this case. Ionization isomers, well, what's on the outside could be on the inside, covalently bound. So these have the same chemical formula, but there's a big difference, right? Bromine has a covalent bond to cobalt in this top complex, and now sulfate has a covalent bond to cobalt. And so we call these ionization isomers because, yeah, who's the counter ion? Sulfate here, it's just ionically bound. And down here it's bromide this time. So, and that's, again, who's being attached, which atoms are attaching together is constitutional. Cobalt to bromine, or is it cobalt to oxygen, I think is down here. Not bromine. Okay, so this is the only stereoisomer you have to worry about. These two, they're called geometric isomers, cis and trans. The trans is the easier one for remember. This is opposite. So do you see the two chlorines are linearly, 180 degrees apart? They're opposite. That makes them trans. The bond angle between, among the chlorine, cobalt, chlorine is 180. It's a straight line, let's say, between the two groups. The two chlorines here are not a straight line. In fact, cis means together, sort of like on the same side. That's how I remember it. Cis sort of looks like short for sister, cis, and I think of it as same side. So the chlorine, the two chlorines are on this side. The far side doesn't have any chlorines, are together on this side. Whereas trans, like you go transcontinental from one side of the continent to the other. Transcontinental Railroad went across the continent. What else is trans? Transfer things from one to the other, it's opposite. So go from one side of the molecule, top side down to the bottom side, going across the entire molecule. That's a trans isomer. Another way of thinking about it is if you have these octahedral complexes, 6 bonds, that's this geometric shape, an octahedral geometry. If you have things making a right angle, that's the cis form. And 180-degree angle, that's the trans form, right? So you could say that these two water molecules are cis to each other. You could say that this water and this chloride are trans to each other. But if you're talking about, well, what's the whole molecule shape? How are these different? Well, the difference is the two chlorines are cis and the two chlorines are trans. Okay, enough said, I hope. All right, linear learning check. Let's go to the other program. Take a look at this. Oh, yeah, the octahedral complex. This is a better drawing. Do you see how this side and that side are 180 degrees apart? So if you put two groups here, that would be trans. If you put one here and there, that'd be trans. If you, let's erase some of that. If you put one group here and the other group there, now they're cis to each other, right? It's a 90-degree bond angle. If you put one group here, one group there, that's 90 degrees. That's also cis. Okay, cool. Eight. Where's 5? Sorry. Wow. Someday I'll learn how to edit videos so I can take all this dead space out. I didn't copy and paste it. This is right on the screen. Okay, I'll let you do A and B. So the question asks, hey, platinum +2 forms a square planar complex. Platinum 4 gives octahedral complexes. Okay, so if it's square planar and platinum, you got platinum in the middle, and then you're going to have 4 groups If we're looking down on the molecule, it's going to be a flat square. So you got, you know, a group here, 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 and there. But if it's octahedral, then you have a vertical set of bonds, and you got something fading into the distance and something coming out towards you. That's octahedral. And what's kind of cool is you're told, you don't have to memorize this, that if it's a +2 platinum, it's square planar. If it's a +4 platinum, it's going to be octahedral. All right, that's a good clue. How many geometric isomers? Okay, so geometric means cis and trans. Why don't you think about A and B? Pause the video. Turns out this one is going to be a platinum. Where's my 5? Yeah, this is a +2. So this is going to be square planar. Platinum has 1 chlorine and 3 ammonias. And whether you put the chlorine in the top right or anywhere else, it's the same molecule. Just spin this. There's only 1 isomer. There is no cis-trans. For B, pause the video, give it a try. This one's a +4. And there are 5 chlorines and only 1 ammonia. It turns out it doesn't matter where you put the ammonia, it's only 1 molecule. So if you put the ammonia up here and the chlorines everywhere else, and if you put the ammonia over here, it doesn't matter. You don't have any cis and trans isomers. For C, pause the video, give it a try. Okay, we're missing brackets, and what that means, the whole thing is your coordination complex with a net 0 charge. So there's no charge of ammonia, the chloride's a -1, the nitro group's a -1. Again, you'd have to rewind the video to see the top of the sample test to look at the charge for NO2. Okay, there's 2 of them here. There's a net 0 charge, so a -1, -1. Platinum, I don't know what you are. We'll figure it out. It equals 0. And so x -2 equals 0. X, this is a +2. Okay, square planar. Okay, now we could put PT here and square planar. We could choose put the 2 ammonias on the left and then put the chloride here and the nitro here. And this is the cis isomer. The 2 identical groups are together. That's how I like to think of it. Or you can put them apart from each other. Now that's trans. And then if you want to put the chloro down here or the nitro, doesn't matter. Remember, these are 3-dimensional molecules. If you built a model kit, it'd be flat and you can just flip it upside down or rotate it. So if you didn't draw it this way, that's okay. Just look and see your orientation of the amines, the ammonia molecules. If they're straight across, that's trans. If you got them side by side, 90 degrees apart, that's cis. Let's do this one up here. Pause the video if you like and give it a try. Ammonia is neutral, chloride's a -1, bromine's a -1, and there's a net +2. I don't know what platinum is, it's my x. X -2 equals a +2, x equals a +4. Okay, so it's octahedral. So put platinum here, and we got bonds here, here, and here. Okay. The ammonias are going to go in 4 bonds. So now let's think about how do we want to orient the halides, the chlorine and the bromine. Do you want them side by side, cis? I put them here, but if you put them up there, over here, as long as they're 90 degrees apart, that's your cis isomer. And then if you put them opposite, so maybe I'll put them top bottom, but you could put, the chlorine here and bromine there, as long as they're 180 apart, that's your trans. But maybe you put them up and down. Maybe that's the easiest to see. Whoops. Yeah, that's right. The ammonia is everywhere else. Now that's as far as I require on my tests. If you want to know about optical isomers, there's a mirror plane here, and there's another form. No, let's not even do that. There is another one here. If you want, you can ask me about that or email me about it. There's an optical isomer pair of enantiomers here, but let's not do that. Okay. Oh, I have to, darn it. Let's clean the page. There we go. There we go. Optical isomers. We're going to skip that. We got the cis and trans. Oh, this is clever. So we're using the ene group, the bidentate, 2 bytes. So here's the ene group side by side with the other ene group. So that's cis. These are mirror images of each other. So I guess we'll just point out it's not on the test, but this molecule on the left is different from the molecule on the right. You have to build models, or you have to think three-dimensionally really well. If you built this model and built that one, you couldn't actually get things to line up on top of each other. If you try and superimpose them, you discover, wait, things just don't line up. They are, in fact, different molecules. They have different properties. Transform, though, the ene group's exactly 180 degrees from the other one. Yeah, that's a transform. Doesn't have optical isomers. Anyways, enough said. Ooh, okay, here's the last. So that was the first part, just about the introduction of coordination complexes, naming them, writing their formulas, and then the cis and trans isomers and the linkage isomers, right? Which atom's connecting? Was it N or the O? And the other one was, we had linkage and, ionization isomers, right? So which one was bound and which one wasn't? Real quickly. Yeah, who's covalently bound? The bromide here, and then sulfate was there. Those are different molecules, ionization isomers. And then we had the linkage isomers, connect through nitrogen or connect through oxygen. And all isomers have the same chemical formula. Okay, enough with that coordination complex. Let's go into crystal theory, crystal field theory. This came about because we see that a lot of the complexes have different colors. And there's 2 ways you can change color. So if you're into dyes and pigments, and you like color and you want to make your own inks or paints and stuff, you could play around with the coordination complexes and develop new colors. It's really cool. This is the theory that helps us predict it and explain it. Okay. So it's all about the d orbitals. That's why we're looking at coordination complexes and transition metals, the d block. Do I want to start with this? I guess I have to. Okay, let's look at octahedral complexes. So where's my pen? This is not on the test, but a lot of us need to understand what's going on so that we can remember it. Okay, so let's draw. What do we had before? We had cobalt, and I don't know. What do we want to put on here? Let's do it this way. Let's put on the cyanide ion, because I know that one works really well. These are supposed to be wedge bonds. And here, I don't know, just put a water molecule. Whatever. That's an octahedral complex, right? Octahedral geometry. Coordination number 6, 6 covalent bonds. Okay. Now, why does this have a particular color and other molecules have different colors? Well, it has to come from the fact that these covalent bonds are bonding to the d orbitals. And here they are. Okay. So there's, right, remember when we did the electron configuration with argon, then we said the 4s, and then we had the 3d, right? There were 5 orbitals. Here are those 5 orbitals. 1, 2, 3, 4, 5. And so what we're saying is that if you put an electron here, that let's say the electron gets to hang out in these 4 lobes. That is one of the d orbitals. It's called dx squared minus y squared. If you put another electron in here, excuse me, maybe you can do this figure 8 dance and hang out in the donut. The electron will be found somewhere in these volumes, what is it, 90% of the time? If you put an electron here, now it does the cloverleaf dance, sort of like this one, swinging these lobes, but they're in between the axes. These are along the axes, but these are fitting in between. Why is that? So that these electrons, as they fly back and forth, they're not going to collide with these. The lobes are not overlapping. And then if you put an electron in this 4th one, now you do the cloverleaf dance this way, but this lobe is set over here and over here. They don't overlap. And of course, over here, you got these lobes that are tucked in between all the gaps. Nobody's overlapping. Okay, so that's what's happening. So this bond right here is probably, well, it's actually a hybridized orbital, right? So we had to make this octahedral, so it's sp3d2, right? The hybridized orbital. So we're taking the Ds and we're mixing up, making hybridized orbitals out of them. Have I lost you yet? Sorry, I'm over-explaining things. Here's the idea of how we can explain different colors. You got the d orbitals, and the d orbitals have different orientations, right? We just said how this lobe lies above this one, so it doesn't overlap. Specifically, these 2 orbitals actually lie on the axes. So when you have a ligand here on the axes, it's bumping into these electrons. And if you have ligands on these bonds, they're going to bump into these orbitals. That's going to create some steric crowding, just some crowding, and it's going to make them more unstable, higher in energy. For groups that are in between, or rather the orbitals, like this, let's see, this one, this is most obvious to me. This orbital is in between. It's not bumping into ligands. It has more room. It's more stable. It's going to be lower in energy. These 2 are going to be high in energy. These 3 are going to be lower in energy. And it has to do with the fact that this donut is lying on the axis, where the electrons that are flying around, and this dz squared can bump into the ligands or be repelled by their electrons. Whereas if electrons hanging out in one of these orbitals, they're enjoying more room, it's roomier, more elbow room. They're stable, more stable. So 2 are going to go up in energy, the other 3 are going to go down. That's the bottom line. That's the crystal field theory. Didn't have to memorize that or anything. It's just trying to explain what do we mean when we go to the next slide. Go to the next slide. There we go. I don't know why they switched the boxes, but what we're doing here, pen please, is remember we said, hey, let's go map out the electron configuration. We got the 4s squared and we had the 3 Ds. Okay, instead of writing it this way, we're going to say, okay, you got the argon, you got the 4s squared, and then you got the Ds, and you don't put them all in a row because now they're not of equal energy. 3 of these are going to go down in energy, and the other 2 are going to go up. The ones that are crowding out go up, these 2. So you got 2 up here, and you got 3 down here. And they're all 3d orbitals. We're not going to call them that anymore. Well, yes, we are. There's other names for them. There's the EG, the T2G. I'm not going to really use those. I just want you to know that 2 of them go higher, 3 of them stay down lower. That'll be good enough. The energy difference depends on 2 things. the identity of the metal ion and your ligands that are attached. Okay, that's the biggest, and that's the most important feature of the CFT, the crystal field theory, is that the 5d orbitals are going to change their energy levels. 2 of them go high, 3 of them go low. And how far apart they are depends on which metal ion you're using and which ligands are attached. Okay, so we got the iron, 2+ ion, if you can read that, it's pretty small print. Good. And here it's just doing normally. We got, this is the 3d orbitals, right? And there must be 6 electrons there. That's how they fill them up. And then when you attach water, well, 2 go up and 3 stay down low. And that's all you do. You just keep these 3 down low and bump these up higher. You got it. If you put on other ligands like cyanide, there's more crowding, there's more interaction, and now there's more steric crowding. These 2 are even more unstable. They even go higher in energy. And now remember when we talked about how much energy it took to pair these up because they repelled each other? They don't like being side by side. Nature now has a choice. She can say, hey, should we keep these unpaired and push them way up here in the high energy orbitals? Or we would just take a little hit and, it's going to take a little bit of energy to pair them up, but at least everybody gets to stay down low in the lower lying orbital. And that's what happens. So at some point, depending on your ligand strength, so there's some strong field ligands, which cause this gap to get really big. Cyanide, ene, and ammonia are those 3. And everything else will be the weak field ligands, where they'll just have a small gap. So essentially what you do is you look at the normal electron configuration with no ligands, and when it's weak field, just take those 2 and bump them up, keep the other 3 down low. However, if you have these 3, or more technically speaking, let's go to the full list. Let's go to the sample test. Okay. Yeah, actually, there's going to be 5 of them now. So it still ends with ammonia. Ammonia, ene, nitro, cyanide, carbonyl, it says right there. Those are going to be the high, yes, the strong field ligands, the ones that make big gaps. From water, there you go, just remember water, neutral water. Water down low, you have a small gap. It's weak field ligands. And that's pretty much it. There's some consequences of that, but if you can remember that part, you're golden. You'll be good. You'll be set for the exam for those types of questions. Other terms, okay. So remember, so it's the same idea. If you have the weak field ligand, small gap, then you keep everything the way it was. Things are not pairing up. And now you look and say, wow, there's a lot of unpaired electrons. There's a lot of spin here, right? Remember, this is the spin quantum number. The spin is pointing up or spin is pointing down. There's a lot of electrons that are pointing up. There's more pointing up than pointing down. So the total number of unpaired electrons is high. So you can also call this the high spin complex. If you have a big gap, a strong field ligand will make a big gap. That'll force all electrons to start pairing up. And now nobody's, in this example, no one is unpaired. There's no unpaired electron, so it's very low in spin. Everything's all paired up. All right, so let's give that a try. Draw a crystal field theory, crystal field orbital energy diagram. So basically just look at your d orbitals and predict the number of unpaired electrons for each of the following complexes. Okay, I don't think I copied and pasted this. Nope, I didn't. We'll just draw it up right here. Okay. Chromium, Remember how to do the periodic table to get the number of electrons just in Cr? And then we want to do it in the cation. You don't have it memorized yet, but ene has no charge. It's neutral. Go back 2 slides. Oh, I can't go back 2 slides when I'm inking it up. Okay, we do need to go. Let's clear this out. Close it up. Do a screenshot. Go over here. Yeah. Oh, let's do it way over here. We have some room. Huh, not there. I need that space. Do it here. Let's shrink the screen. So, is anyone still listening? Because you can fast forward it to the point where I start drawing again. Let's go get the periodic table. There's one. Control C. Paste. And let's go get top of the periodic, top of the sample test right here. Just need this part. Okay. Okay, welcome back. Okay, let's try this again. Number 7 on the learning check. Okay, chromium. We want to find its original electron configuration. It's also one of the exceptions. So as you look at chromium here, element 24, we're going to write argon, and then it's going to have the 4s electrons, 2 of them, and then it's going to have 1, 2, 3, 4 d electrons. Okay, so let's get the electron configuration. It's argon, it has a 4s squared, and the 4 d electrons, weight, that's almost a filled orbital. So in fact, this is the exception. Chromium and copper are the exceptions we'll have to remember. 4s1, 3d5. Cool. And now, what's the charge on this chromium? We'll go up here to the top of your exam, sample test in this case. The ene has no charge. NO2 has a -1. Ammonia has no charge. Ene has no charge. So the whole complex has a net charge of +3. That means the chromium is carrying all that charge. So lose 3 electrons. So take away the s electron and 2 more. And now we have the electron configuration. It's 3d3. Cool. Okay. How many groups are on there? It's ene. Ene, ethylene diamine, is bidentate. Yeah, remember it bites twice. Has 2 groups. So I know it's 3 molecules, but what's its coordination number? It's bidentate. It bites twice. Each ene makes 2 covalent bonds, and if there's 3 of them, it's got a coordination number of 6. Before hashtag the number sign, the tic-tac-toe meant number. Okay, so you'll need to know that. You'll need to know, let's see, oxalate, it's on the full list, and ene are bidentate. I think those are the only ones. Okay, so coordination 6. So you got to put 6 groups on here. How you get 6 groups on here? Well, it's got to be octahedral. Okay. Do we need that? I don't think so. Sorry, overanalyzing. What do we have to do? We need the crystal field orbital energy diagram. It's octahedral. So if you take more chemistry, that's when you have to look at the molecular geometry. because your energy diagram might change. But in this class, if we're doing crystal field theory, we're just going to do 2 up, 3 low. And those are your d orbitals. Okay, and now that we know it's chromium with 3 d electrons, now we can put them in here. Do we have a big gap or a small gap? Well, the ene is before water. So it's a strong, that's what this series means, the spectrochemical series. We got the strong ligands first. So we have a big gap or a large gap, which means you need to pair things up before you start putting electrons up high. This is a strong one. Water starts the weak ones. Weak this way. That's when you have a small gap and you spread out all electrons among all the orbitals before pairing up. Ene is strong, so put them down here, and we just ran out before we could pair up. So there it is. We got it done. Predict so there's the orbital energy diagram right here. That's kind of nice to see that it's large. So on the test, that would tell me that this is a strong field ligand, making a large gap. Predict the number of unpaired electrons. Well, just count them. There's 3 unpaired. Done. All righty, let's try Mn with cyanide. Well, what kind of field ligand is that? One of the strongest. Okay, so that's strong field. There's 6 of them. It's octahedral again. What's the charge on manganese? Let's go there. Well, the net charge on the complex is a -3, but the cyanides right here, that's a -1. So there's 6. There's a net -6 charge from the cyanides. The magnesium is unknown. And the whole thing adds up to a -3. So X has to be a +3. So what's the electron configuration of manganese when it's a +3? Well, let's do the ordinary manganese 0, the neutral atom with 25 electrons. It's going to be 4s2, 1, 2, 3, 4, 5, 5 d electrons. So Mn has 4, the 4s electrons, and then 5 of these. But to make a +3, you lose the 2 s's and 1 of these. It's 3d4. Okay, and then we got 3 down low, 2 up high. What kind of gap do we have? Strong field gap. It's right at the beginning. So we have a large gap. So that means you have to pair up and fill the bottom before you add electrons to the top. We got 4 electrons to fill into this orbital diagram. So 1, 2, 3, spread them out first. And then now we have to decide, do we put the 4th one up here? No, the gap's too large. Keep it down here and pair it up. Done. And that should not be a full arrow, that's a half arrow. Okay, how many unpaired electrons do we have? Well, they're paired up here. We have 2 unpaired electrons. Nice. Let's do cobalt. Water has no charge. The whole thing's a +2. Well, that means cobalt carries the full +2. What's the electron configuration of just cobalt? Let's go find out from the periodic table. Cobalt's element 27, so you got the 4s squared, and then 1, 2, 3, 4, 5, 6, 7 electrons. It's 3d7. And the ground state for the neutral atom, 4s squared, 3d7. And then you lose 2 electrons, so lose the s electrons first, so it's 3d7. Okay, and it's 2 up high, 3 down low. What kind of gap do we have? It's water. That's the break point. That's the start of the weak field ligands. That means you have a small gap. So spread them all out, 1 electron each before pairing. How many electrons? 7. So 1, 2, 3, small gap. So go ahead and put them up here. I got 5 electrons, 1 in each. There's 2 left over for 7. So now pair up on the bottom. There we go. That's the electron configuration for that complex. How many unpaired electrons do we have? 1, 2, 3. Those are unpaired. 3 unpaired electrons. Nice. Cool. All right. Back to the PowerPoint slides. Okay. Okay. So again, if you take more chemistry, you have to know the molecular geometry to get your orbital diagram correct. Here it's 3 up, 2 down. We're not going to do that, but it exists, right? So if your complex is tetrahedral, not octahedral, then your orbital diagram changes. Why? Gosh, it's optional, but if you go back to this diagram, when you're octahedral, when you're tetrahedral, now your 4 groups are lining up with these, and they're not lining up with these 2, right? Octahedral is on the axis. The tetrahedral is in between the axis where these 3 are. So now these are bumping into your ligands, and the first 2 are not. So that explains why this flip-flops whenever you go to tetrahedral. But sorry, that's not on the test, but it makes some sense. Square planar, there's even another diagram here. Again, it just depends on who's bumping into who. And it wasn't 3 up, 2 down, it's 2 and then 3 stack up like that. Yikes. Not going to cover it. Why were we counting up those unpaired electrons? Right here to explain magnetism. This is cool. So paramagnetic don't go away. Paramagnetic compounds are the ones you're most familiar with that make up real magnets in everyday life, right? So the refrigerator magnets, or what else? A horseshoe magnet or a compass. Those types of magnets, they're made of materials, mainly iron because it's cheap, readily available, and these materials that make up magnets, there are a lot of unpaired electrons that make the material paramagnetic and act like a magnet. If all, and that's a key word, if all the electrons are paired, then it's diamagnetic, right? So what kind of material is this, diamagnetic or paramagnetic? Well, I see at least 1 unpaired electron. That makes it paramagnetic. How about this complex? Still made with iron. This is iron with water, iron with cyanide. Everybody's all paired up. There are no unpaired electrons. This material is diamagnetic. It's going to make a lousy magnet. This material could make a good magnet, which is kind of interesting. If you have these 2 molecules in solution, you can put a magnet in there and attract these away from those. Cool. All right, so that, as quickly as we went through that, is still pretty important. So definitely know how to identify diamagnetic and paramagnetic materials. You're going to have to draw these orbital diagrams, put in the electrons, and see if you're left with any unpaired electrons. If there's even one unpaired electron, then yes, paramagnetic. If all of them are paired up, then it's diamagnetic. Cool. That's not too bad. Okay, for which the electron configurations, will there be a difference between high and low spin configurations in octahedral complexes? Well, a loaded question. We'll do that in a second. No, we're going to go and do it now. Thought there was something else. I'm not going to ask you that question on the exam, but it is one we should just work out to figure out what the heck are they talking about. So here's the question again. Oh, high and low spin configurations. There are all these terms. So let's break down the terms one more time. Okay, so for our exam, if we're going to do the crystal field theory, we're only going to be looking at octahedral complexes. And for that one, it's 2 high and 3 low. Then you need to know about the gap size. If it's small, that's because we have the weak field ligands. And if it's large, it's because we have a strong field ligand, or ligands, plural. Okay, I really encourage you just to memorize that part. You're going to get that list on the exam somewhere. There it is, your spectrochemical series. And on the left, the greater than sign, these are your strong field ligands. And then starting with water to the right, those are your weak field ligands. Okay, so you'll have that information. This will help you work with that information. Go up. So that's what I encourage you to remember. Size of the gap, strong field, strong really pulls them apart, really big. Okay, from there you can get the other definitions. So we got something called a high field and low, high spin and low spin. Well, if you're weak field, that's where you keep them unpaired, right? So if you have a molecule that's D5, metal ion that's D5, then when it's a weak field and small gap, the most stable configuration is where you don't pair them up because it takes energy to pair them up. Electrons repel electrons. You spread them out. So do we have a lot of spin here? Do we have a little bit? This turns out to be high spin. Is it paramagnetic or diamagnetic? Well, this one's paramagnetic. There's at least one unpaired electron. Okay, if we still have D5, you always fill up the bottom orbitals one at a time, and now you have a choice. So you go way up here for the 4th electron. No, that's way too much energy. I know it hurts a little bit to pair them up, but it's less energy to pair them up than it is to bump it way up in the gap. And now right here. So how much unpaired electrons do we have? Not much. This is the low spin. And is it paramagnetic or diamagnetic? It's still paramagnetic. There's one, at least one, and actually there's only one unpaired electron. Now this is saying for which d electron configurations, I just did the D5. And for D5, is there a difference? Yes, right? We have 5 unpaired versus 1 unpaired electron. There's a big difference. So where are there other differences? Well, we got the small gap versus the large gap. And if you do D1, you got the same configuration, right? The lowest orbital has 1 electron, lowest orbital has 1 electron. There's no difference. If it's D2, there's no difference. This diagram is the same as that diagram. I know those are higher, but just look at the field, the orbitals with electrons, it's a match. The lowest 2 have electrons, and so is the D3. There's no difference. No difference between the 2 with the strong field or the weak field ligands. But when you get to D4, 1, 2, 3, where's the 4th one go? Do you pair up? Nope, this is weak field. It's easier to put the 4th one there. How about on the high sorry, on the strong field, no, it's way too high. So you do pair them up. Now they're different. And that's what the question is asking. The D4 configuration gives you differences. The D5 gives you differences. Can I just switch to a different color? If we do okay, there's D5, D5. If we do D6, that's D6, and they're different. Is this compound paramagnetic or diamagnetic? Well, that's supposed to be an upside down arrow. There's nobody unpaired. This material is now diamagnetic. How about this one? Oh yeah, still paramagnetic. Cool. All right, D4, D4, D5, D6, they're all different. D7, I think is still different. I think you can do the rest, right? But that's what the question is asking. Once you get to D8, yeah, once you get D8 versus those two, right? So 1 electron, 1 electron, 2 electron, 2 electrons, 3 electrons, 3 electrons, 4 electrons, 4 electrons, 5 electrons, 5 electrons. D5 is different. 6 electrons, still different. 7 electrons. Well, now you have to put this one up here. There's no more room. And, oh yeah, 7 electrons still the same. 8 electrons. Oh, 8 electrons is the same. I know the gap is bigger, but what's the configuration? Lowest orbitals, everyone's all paired up. Highest orbitals, there's one each. And then D9, you're just going to pair up this one and that one. D10, everybody's filled. So D8 through D9 to D10, they're all the same again. Cool. All righty. Let's go back to the PowerPoint slides. Oops, I forgot sharing. Okay, let's talk about color. We have the big gap and the low gap. So what is color? Color is light. And so if you want, if some material is colored, we shine white light on it, and that material will absorb some of the colors of the rainbow. And the colors that don't get absorbed pass through, and that's when we say, oh yeah, this material has this color. And it's actually the opposite. So a red apple is actually absorbing all the colors except for red. And so we shine white light on a red apple. All the colors except for red get absorbed and sucked into the apple skin, if you will. And then what gets reflected off of the apple is red light. And so we say, hey, the apple's red. But it really isn't. It's all the colors except for red. It's only reflected. And so how does light get absorbed? Well, light has energy. E equals h nu from physics. And the energy of light gets absorbed, annihilated. The light gets totally absorbed and it's gone. But the energy can't destroy energy. The energy of the light has to go somewhere. The energy goes into electron in a ground state, lower energy orbital, and it can jump up to a higher energy state. And the rules are, nature, she makes the rules, that's rule number 1. But the rules are that if the energy difference between one orbital and the other exactly matches the energy of the light ray, then the light can be absorbed. And if the light doesn't exactly match the energy gap, the light will just pass through. It'll be transparent to that wavelength of light, that energy, that amount of energy of light. So here is different ways to make different compounds. One idea is change a metal. So the ligands are all the same. This is all water bound to cobalt, water bound to nickel, water bound to copper, water bound to zinc. And these all have different colors. Zinc, you actually said, I would hope you see, has no color. What's going on there? Well, that's kind of interesting. So zinc is the last transition metal on the periodic table. There's 10 electrons in zinc, right? So zinc has the 4s squared and the 3d10. This zinc is a +2 cation. Water's neutral, right? So all the charge is produced by the zinc. So lose those 2 electrons and it's 3d10. Water, remember that's where the weak field ligands start up. So there's a small gap, but there's 10 electrons. I'm filling it incorrectly, sorry. Let's do that again. It's a weak field, so a small gap. So there we go. That's how the electrons are supposed to populate the orbitals. Spread them out, then pair them up. Okay, and then shine light on this. And let's say we match the gap. This electron potentially could absorb the light ray, but it needs to bump up to this orbital. There's no room. So no light gets absorbed. For copper, remember copper is the exception. It had 4s1, 3d10, but this is copper 2+. So take out the 4s and one of these, 3d9. Water's still the weak field, so the gap is small. Put in 9 electrons. Got 5, 6, 7, 8, 9. Now you can shine light on this, and one of these electrons can be bumped into this spot right here. And if you match the light with the size of this gap, the light that doesn't get absorbed is what we see. And the gap changes depending on which metal ion you're using. Cool. You can also change the color by changing the ligand. So here's nickel 2+, nickel 2+. We got water, weak field. Not much color there, I don't see any. I'm partially colorblind, so don't ask me about colors. But I do see some color differences in these last two. I'm not gonna guess. Oh, yes, I am. Is this blue and that's purple? I don't know. They're different. But we got ammonia here and the ethylene diamine. So changing the ligand, keeping the metal the same, the charge, oxidation number of the metal the same. If you change the ligand, that also changes the gap. And then the light, the wavelength of light that's going to be absorbed. And so you absorb different colors. I'm sorry, you absorb different wavelengths. Those are different colors. Remaining colors are the colors we see and say, hey, this solution, I don't know, looks purple to me. We're not going to get into this on the exam, but this is how you can figure out, you can look at the color spectrum or a color wheel. And let's say the copper is blue. And so what's happening is that copper is actually absorbing the orange light out of white light. So orange colors are being removed and the blue is getting through, not being absorbed, and that's what we see. The green nickel, so what it's doing, it's absorbing the red wavelengths. So the red's getting taken out, leaving the green behind, that's what we see. Cool. And that's just more variety. Change the metal, change the color, change the oxidation state, change the color, change the ligand, change the color. So there's 3 ways to vary the color. Lots of variations, lots of possibilities. So again, you could go into color chemistry and make all different types of pigments and different color solutions by playing around with which metal you want to work with, which oxidation state for the metal, and which ligands. Very cool. All righty, how are we doing? 46. Let's see how far we have to go to the end. No. Okay, the rest of this is just talking about specific metal complexes, but we're not going to cover that or put that on the test. So let's just end with this learning check number 9. And we'll go and do that on the other sheet over here where I have more room. Thanks for staying around. I won't tell everyone if you had to stop and pause this and come back later. Apologize, it's gone a long time. But here we go. Nice summary page. Let's name this compound. Okay. So we get the periodic table. So if you don't know what K is, you can go look it up. It's potassium. And each one of those potassium has a +4 charge, sorry, +1 charge, so there's 4 of them. Manganese, don't know its charge, but fluoride is fluoro, and there's 6 of them. Let's see, I'm going too fast. I want to be done too. Start all over. Okay, outside the complex, there's a +4, so that means inside, the whole thing must total a -4. Within the complex, manganese, Mn, I don't know what your charge is, but there's 6 fluorides, each with a -1. The manganese -6 has to equal -4. Well, then that must be a +2. 2 minus 6 is a -4. So the oxidation number of manganese is a +2. Okay, so let's name it. The name of this is cation first, then anion. The cation is potassium. And then the name of the complex, the stuff in brackets, alphabetical order of the ligands. Well, there's fluorine or fluoro. There's 6 of them, so you have to say hexa. 6 fluorines, hexafluoro. I got that memorized. But if you go back and look at the top of the exam, you'd see F minus, the name for that is fluoro. Go to the periodic table and get manganese, but before I write E's of manganese, the whole thing has a net -4 charge. So you have to add 8. So it's manganate. And then the oxidation number is a +2. There we go. There's the name of the complex. What's its geometry? So start by asking, what's the coordination number? How many teeth are biting into the manganese? How many covalent bonds? There's 6 fluorides. Fluoride, remember the fluoride only bite once. We just had to worry about the ene and the oxalate, oxalato. Those are bidentate. They bite twice. Bidentate. They attach by 2 covalent bonds. Everyone else, just 1. So there's coordination number 6 fluorides, each fluoride making 1 covalent bond. And when you have an atom, in this case manganese, you want to put 6 groups on it. What's the shape of it? What's the molecular geometry? Or electronic geometry if you want. It's octahedral. Cool. What is its magnetic property? Okay, so that could be on the test. There's 2 words to choose from. It's either paramagnetic or it's diamagnetic. How do you figure it out? You need to get the crystal field theory going. It's going to be 2 up, 3 down low. Is it a big or a small gap? Well, what's fluorine? I don't know. Gotta go look at the spectrochemical series. Where do we put it? Put it right here. There at the bottom of the page. Fluoride, ooh, it's after water. Water is the start of the weak ones, and water is stronger than fluoride, but water itself is a weak field. Fluoride, so are you. So it's a small gap. Why do we need to know that? Because you keep things unpaired. Fill up everything when it's a small gap. It's a weak field ligand. Okay, small gap. How many electrons? Well, what's Mn2 plus? I don't know. Well, what's just regular Mn? Yeah, periodic table. Come and help us out. There's one right here. So start with just the atomic neutral form of manganese. It's element 25, so there's 5 d electrons. So the 4s2 and 5 d electrons. Okay, so regular manganese is argon, 4s2 and 5 d electrons. Take away 2 means take away those. You got 5 electrons. Cool. So put 5 electrons in here. It's small gap, so that means spread them out. 1, 2, 3, 4, 5. Well, what do you think? Paramagnetic or diamagnetic? Nobody's paired up. Well, that's not true. Inside the rest of the electron configuration, everyone else is paired up. But more importantly, you found at least one unpaired. That's making it paramagnetic. Yes. What color would you predict? Okay, that could be on the test too. So I'm not looking, well, you didn't give me the color wheel. No, I just want you to just ballpark idea. And it comes about by your prediction of the gap. So we're going to shine light on this and raise one of the electrons up here, just a little bit of energy. So who has a little bit of energy in the visible light spectrum? Remember, it's like red all the way up to blue, and then it's ultraviolet, and it's infrared. This is weak, low energy, and you can get a sunburn from this high energy of ultraviolet. So this is high energy, strong energy. I can't spell high energy. Well, this is just a little gap, small gap. So it's only a little bit of energy that makes a jump. So this is the tricky part. It's a small gap. So red is absorbed. So you shine white light on the solution, all the red light gets taken away. What are you left with? The opposite of red. If you said blue, I would give you that full color, that full credit. It's actually green. Green's the opposite of red. So the solution is actually green color. There you go. I think that's everything. Thanks for sticking around. I'll see you in the discussion posts or send me an email. Take care.